Good evening. Tonight, you'll discover the most mysterious objects in our universe, places where space and time bend beyond comprehension, where light itself cannot escape. 100 facts about black holes that will guide you into the most peaceful sleep. But first, if you want more journeys like this, subscribe to the channel and leave a like right now, because in just a few minutes, you'll be too relaxed to move. Now then, make yourself comfortable. Let your body sink into your bed. Close your eyes. Tonight, I invite you on a journey into darkness, into the places where stars go to die, where the universe reveals its most profound secrets. 100 remarkable facts, told slowly, gently, without haste. You don't need to remember them. You don't need to analyze them. Just listen and let these words become part of your dreams. Breathe evenly, deeply, and we begin. A black hole is a region of space where gravity is so strong that nothing can escape it. Not light, not matter, not even time flows normally there. Imagine a place where the pull of gravity becomes so intense that the very fabric of space collapses in on itself, where the rules we understand no longer apply. That's a black hole, a boundary in the universe, a point of no return. The term black hole was coined by physicist John Wheeler in 1967. Before that, these objects were called frozen stars or dark stars, or simply gravitationally collapsed objects. But Wheeler, in a lecture at NASA, used the phrase black hole almost casually, and the name stuck because it captured something essential, something about the emptiness, the darkness, the absolute void. Sometimes, the simplest name is the most profound. Black holes aren't actually holes at all. They're objects, incredibly dense objects, all their mass compressed into an infinitesimally small point. Think of it this way. If you could take all the mass of our sun and compress it into a sphere just 6 kilometers across, you would have a black hole. All that matter, all that substance, crushed down into something almost impossibly small. The boundary around a black hole is called the event horizon. The event horizon isn't a physical surface. It's a boundary in space, the point of no return. Cross this line, and you're gone. Forever. There's no coming back. No escape velocity fast enough. No force strong enough to pull you out. It's called an event horizon, because beyond it, no events can be observed from the outside. It's the horizon of knowledge, the edge of what we can know. At the center of a black hole lies something called a singularity. The singularity is where all the mass is concentrated, a point of infinite density, where our physics breaks down completely. We don't really understand what happens at a singularity. Our equations produce infinities. Mathematics itself seems to give up. It's a place where, perhaps, the universe admits it has mysteries even math cannot solve. Interesting, isn't it? Black holes come in different sizes. The smallest are called stellar black holes. These form when massive stars collapse. They can be just a few kilometers across, but contain the mass of several suns. Then there are intermediate black holes, hundreds or thousands of times the mass of our sun. And then there are the giants, the supermassive black holes, millions or even billions of times more massive than our sun. These lurk at the centers of galaxies. Each size tells a different story of the universe. Black holes rotate. Almost all black holes spin, some slowly, some incredibly fast, rotating at nearly the speed of light. This rotation drags space and time around with it, like honey swirling around a spoon. It's called frame dragging, near a rapidly spinning black hole. Space itself is pulled in the direction of the spin. You couldn't stand still even if you wanted to. The universe itself would be moving beneath you. You cannot see a black hole directly, because no light escapes. They're invisible, pure darkness against the black of space. But we can see their effects. We can see matter spiraling into them, heating up, glowing brilliantly just before it disappears forever. We can see stars orbiting around nothing, moving in ellipses around an invisible point. Sometimes, what we cannot see tells us more than what we can. The gravity near a black hole creates something called spaghettification. That's the actual scientific term, spaghettification. If you fell toward a black hole feet first, the gravity pulling on your feet would be so much stronger than the gravity pulling on your head that you'd be stretched, pulled like taffy, like spaghetti. Your atoms would be pulled apart, stretched into a long, thin stream. It sounds frightening, but rest easy. You're safe here, far from any black hole. Time behaves strangely near a black hole. The stronger the gravity, the slower time flows. Near a black hole's event horizon, time slows to a crawl. If you watch someone fall into a black hole, you'd see them slow down, slower and slower, moving like molasses, until they appeared to freeze at the event horizon. But from their perspective, they'd fall through normally. Time is relative. Einstein taught us that. And near a black hole, time becomes almost meaningless. Most black holes form when massive stars die. When a star much larger than our sun runs out of fuel, it can no longer support itself against its own gravity. The core collapses in an instant, in less than a second, and the outer layers explode outward in a supernova. But the core keeps collapsing, crushing down, becoming smaller and denser, until it becomes a black hole. A star's final act is to disappear. Not all stars become black holes, only the most massive stars at least 20 to 25 times the mass of our sun. Smaller stars become white dwarfs. Medium stars become neutron stars. But the giants, the true giants of the cosmos, they become black holes. It takes a tremendous amount of mass, a tremendous amount of gravity, to compress matter beyond the point of no return. The collapse happens incredibly fast. Once the core of a massive star begins to collapse, it takes less than a second. One moment, a star's core. The next, a black hole. The transition is nearly instantaneous. In that brief moment, the heart of a star vanishes from our universe, crosses the boundary, becomes something else entirely. Imagine that. A star that burned for millions of years, gone in a heartbeat, before the collapse. Massive stars create the heavy elements in the universe. In their cores, they forge carbon and oxygen and iron. Through nuclear fusion, the pressure and heat creating new elements. When they explode, these elements are scattered into space, seeding the cosmos with the building blocks of planets, of life. So black holes, in a way, are connected to our existence. The explosions that create them also create the elements in our bodies. We are, quite literally, made of stardust. Supermassive black holes form differently. The giants at the centers of galaxies didn't form from single stars. They're too massive for that. Scientists believe they formed in the early universe, perhaps from the direct collapse of massive gas clouds, or from the merger of many smaller black holes. We're still learning, still piecing together the story. But these ancient objects formed when the universe was young, when galaxies were first taking shape. They're among the oldest structures in existence. If you're still awake, that's perfectly fine. Let these words wash over you. Some black holes may have formed right after the Big Bang. These are called primordial black holes, theoretical objects that might have formed from density fluctuations in the early universe. They could be tiny, smaller than atoms, or they could be massive. We've never detected one for certain, but they might be out there, scattered through the cosmos, remnants from the first moments of time. The universe keeps its secrets. When two black holes collide, they merge, they spiral around each other, faster and faster, creating ripples in spacetime, gravitational waves that spread across the universe, and then they touch, they merge, becoming one larger black hole. In that moment, they release more energy than all the stars in the visible universe combined, but not as light, as gravitational waves, as ripples in the fabric of space itself. We've detected these mergers. In 2015, scientists detected gravitational waves for the first time from two black holes colliding 1.3 billion light-years away. The signal lasted less than a second, a chirp, a brief pulse, but it told us about an event that happened over 1 billion years ago. By the time we heard it, the black holes had long since merged. The waves had been traveling through space for longer than complex life has existed on Earth. Black holes can evaporate. This was Stephen Hawking's great discovery. Black holes aren't entirely black. They emit radiation, very slowly, very faintly, over unimaginably long time scales, trillions upon trillions of years. A black hole can lose mass, shrink, eventually vanish entirely. But for the black holes we know about, this process takes longer than the current age of the universe by many, many times over. They're effectively eternal. For now, as a black hole evaporates, it gets hotter. Smaller black holes evaporate faster, and as they shrink, they radiate more energy, get hotter and hotter. In their final moments, they might explode, releasing all their remaining energy at once. But again, this is so far in the future that the stars will have all burned out. The universe will be cold and dark. Black holes will be among the last things to go. At the center of almost every large galaxy, there's a supermassive black hole, including our own. The Milky Way has a supermassive black hole at its heart, called Sagittarius A star, pronounced Sagittarius A star. It's about 4 million times the mass of our Sun, and yet it's relatively quiet, dormant, not currently consuming much matter, just sitting there, at the center of everything, holding the galaxy together with its gravity. Sagittarius A star is 26,000 light-years away from Earth. That means the light we see from the region around it left there 26,000 years ago. When that light began its journey, humans were still in the Stone Age, just beginning to create art, to tell stories. The light has been traveling all this time, just to reach us now, tonight. As you lie here, listening, we've taken a picture of a black hole. In 2019, the Event Horizon Telescope, a network of radio telescopes around the world, captured an image of a supermassive black hole, not Sagittarius A star, but one in a galaxy called M87, 55 million light-years away. The image showed a ring of light, glowing matter swirling around a dark center, the shadow of the black hole itself. It was the first time humanity had ever seen one. After decades of theory, there it was, real, visible. That black hole in M87 is enormous. It's 6.5 billion times the mass of our Sun. Its event horizon would encompass our entire solar system. If you could place it where our Sun is, it would extend beyond Pluto, beyond the Kuiper Belt, into the realm of the comets, a giant, a true monster of the cosmos. And yet, it's so far away. It appears smaller in the sky than an orange on the moon would from Earth. Supermassive black holes can power quasars. Quasars are among the brightest objects in the universe, brighter than entire galaxies. They're powered by supermassive black holes actively consuming matter. The matter forms an accretion disk, spinning around the black hole, heating to millions of degrees, glowing brilliantly. Some of that energy is channeled into jets, beams of particles and radiation, shot out at nearly the speed of light, for thousands of light years into space. A quasar is a black hole in the act of feeding. You can picture it if you wish, but let the image be gentle. Let it be distant. Quasars were more common in the early universe, billions of years ago, when galaxies were younger. There was more gas and dust around, more food for black holes. Now, most supermassive black holes are quiet, dormant. They've consumed most of the available matter in their vicinity. They wait, patient, eternal, for the occasional star or gas cloud to wander too close. The most distant quasar we've found is over 13 billion light years away. We see it as it was just 670 million years after the Big Bang, when the universe was young, still in its infancy. And yet, even then, there were already supermassive black holes, billions of times the mass of the Sun. How they grew so large so quickly is still a mystery, one we're working to understand. Black holes can influence star formation in galaxies. The energy from active black holes, from their jets and radiation, can heat up gas clouds, preventing them from collapsing to form new stars. In this way, black holes regulate their galaxies. They're not just destructive, they're part of the life cycle, part of how galaxies evolve and mature, a balance between creation and consumption. Some black holes wander through space. Most supermassive black holes sit at the centers of galaxies, but some have been ejected, kicked out by the gravitational waves from a merger. These rogue black holes drift through intergalactic space, alone, unattached to any galaxy. Silent travelers, moving through the void for billions of years. When galaxies merge, their black holes merge too. Eventually, it takes a long time, millions of years, but as the galaxies spiral together, so do their black holes. They circle each other, closer and closer, until finally they merge, creating an even larger supermassive black hole. And in that moment, they send ripples through space-time. Gravitational waves so powerful, they'll echo across the universe for billions of years. Imagine if you can, but don't strain. Just let the thought drift by. Near a black hole, the laws of physics become extreme, not broken, just pushed to their limits. Gravity so strong, space-time so curved, that our normal intuitions fail. Einstein's theory of general relativity describes what happens, but even that theory encounters infinities at the singularity. We need a theory of quantum gravity, something that unites quantum mechanics with general relativity, to truly understand what happens inside. But we don't have that yet, not fully. Black holes might be connected to white holes. A white hole would be the opposite of a black hole. Nothing could enter it, but things could come out. Some theories suggest that what goes into a black hole might emerge from a white hole, perhaps in another part of the universe. or even another universe entirely. It's speculative, theoretical, but it's a beautiful idea that black holes might be doorways, passages to elsewhere. Some physicists think black holes might create new universes. When matter collapses into a singularity, perhaps it doesn't end. Perhaps it bounces, creates a new Big Bang, a new expanding universe on the other side. Our entire universe might be inside a black hole, in some larger parent universe. And every black hole in our universe might contain entire universes of its own. Universes within universes. Infinite nesting. It's a dizzying thought. Let it drift away, like a leaf on water. The information paradox is one of the biggest puzzles in physics. Quantum mechanics says information can never be destroyed, but black holes seem to destroy information. Anything that falls in is lost forever. Or is it? Hawking suggested that information might be encoded in the radiation black holes emit, scrambled, but not destroyed. The debate continues. Some of the brightest minds in physics working on this problem. What happens to information when it crosses the event horizon? We don't know yet. Inside the event horizon, space and time swap roles. Outside a black hole, you can move through space, but time moves forward inexorably. Inside, you can move through time in different directions, but you must inevitably move toward the singularity, pulled by what appears to be time itself. The singularity isn't a place, it's a moment in your future that you cannot avoid. It's difficult to imagine, and that's all right. Let the strangeness wash over you. Black holes might preserve information on their surfaces. The holographic principle suggests that all the information inside a black hole is encoded on its event horizon, like a hologram. Three-dimensional information stored on a two-dimensional surface. If true, it would mean the universe itself might work this way. Reality might be a projection from a lower dimensional boundary. We're still exploring this idea, still testing it. Falling into a black hole would feel different depending on its size. For a stellar black hole, small and dense, the tidal forces would rip you apart long before you reach the event horizon. But for a supermassive black hole, you could cross the event horizon intact. You might not even notice the moment you pass through. You'd just keep falling toward the center. And only later would the tidal forces become extreme. From inside a black hole, you could still see the outside universe. Light from outside can still reach you. You could look back, see the universe, but it would be distorted, time dilated. You'd see the future of the universe unfold rapidly, but you couldn't send any signal back. You couldn't communicate. You could only watch. A one-way window into everywhere and everywhen. Black holes might have hair. For a long time, physicists thought black holes were simple, defined only by mass, charge, and spin. Black holes have no hair, was the saying. But recent research suggests they might retain more information. Quantum information imprinted near the horizon. This hair might encode what fell in. The universe is more subtle than we thought. We may never fully understand black holes from the outside because we can't see past the event horizon, can't retrieve information from inside. There are limits to what we can know. Some things might forever remain mysteries, hidden behind horizons, beyond the reach of observation. And maybe that's okay. Maybe the universe is allowed to have secrets. Let that thought be comforting. Not everything must be known. Black holes play a crucial role in galaxy formation. The supermassive black holes at galactic centers help regulate how galaxies grow. They prevent galaxies from forming too many stars too quickly. Without them, galaxies might look very different. Star formation might run away, consuming all available gas in a cosmic frenzy. Black holes are architects, shapers of cosmic structure. The Milky Way's black hole is remarkably calm. Sagittarius, A star, compared to other supermassive black holes, is quiet. It's not actively consuming much matter, but every few decades, something does fall in. A star ventures too close, or a gas cloud, and for a brief time, the black hole flares, brightening, before settling back into silence. Scientists track stars orbiting Sagittarius A star. There's one star, called S2, that has a highly elliptical orbit. It comes incredibly close to the black hole, within just a few light hours. By watching S2, year after year, scientists have measured the black hole's mass precisely and tested Einstein's theory of general relativity. So far, Einstein is right, even in the most extreme conditions we can observe. In April 2020, a star passed through the disk of matter around Sagittarius A star. The star, called S0-6, plunged through, and the black hole's accretion disk lit up, glowing in X-rays. It was a rare event, a chance to study how matter behaves near the event horizon. Astronomers watched, recorded, learned. The black hole is a laboratory, teaching us about the universe. Black holes can create gravitational lenses. Their intense gravity bends light passing nearby. This can magnify and distort the light from objects behind them. Sometimes, you can see multiple images of the same distant object, warped around the black hole, formed into rings or arcs. Einstein predicted this, called it gravitational lensing, and black holes create some of the most dramatic examples. Space is curved, and light follows that curvature. Are you still listening? Or have you drifted into dreams? Either way is perfectly fine. Black holes can accelerate particles to nearly the speed of light in the jets they produce, in the swirling accretion disks. Particles are accelerated to incredible speeds. These cosmic rays travel across the galaxy. Some of them reach Earth, passing through you, through me, right now. Messengers from black holes, billions of light years away, touching us, connecting us to the farthest reaches of space. The nearest known black hole to Earth is about 1,600 light years away. It's part of a binary system, orbiting with a visible star. We detected it by watching the star's motion, seeing it pulled by an invisible companion. 1,600 light years sounds close, but it's not really. You could travel at the speed of light for 1,600 years and only then arrive. We're safe, far from any danger, just observers watching from a distance. There may be millions of stellar mass black holes in our galaxy, most of them invisible, silent, not actively consuming matter, just drifting through space. They're the remnants of dead stars, scattered throughout the Milky Way, invisible passengers on the galaxy's journey. We've only detected a fraction of them, the ones that betray themselves by pulling on visible companions or by occasionally feeding. Black holes can strip stars apart. If a star wanders too close, tidal forces can tear it apart. This is called a tidal disruption event. The star is stretched, pulled into a stream of gas. Half of it falls into the black hole. The other half is ejected, flung back into space. For a few months, the black hole brightens dramatically as it consumes the star's remains. Then, it fades, returning to darkness. We've observed dozens of tidal disruption events. Each one is slightly different. Each teaches us something new about black holes, about stars, about the physics of extreme gravity. The universe is full of drama, of violence, but from here, lying in your bed, it's all very far away. Just stories, just facts, gentle words in the night. We can't see black holes directly, but we can see what they do. We see the gas and dust spiraling around them, heating up, glowing in visible light, in X-rays, in radio waves. We see stars orbiting empty points in space, moving in perfect ellipses around something invisible. We detect gravitational waves when they merge, ripples in spacetime itself. The invisible makes itself known. X-ray telescopes are crucial for studying black holes. The material falling into black holes heats to millions of degrees. At those temperatures, it emits X-rays, so we use space-based X-ray telescopes like Chandra, like XMM Newton, to study black holes. They've revealed thousands of black holes across the universe, each one a point of light in otherwise darkness. Radio telescopes help us map the jets from black holes. The jets extend for thousands of light years, glowing in radio waves. We can trace their structure, see how they interact with the surrounding space. Some jets are straight, like arrows. Others curve, twisted by magnetic fields or the motion of the galaxy. Each one a signature of the black hole that created it. The Event Horizon Telescope is actually many telescopes. It's a network spread across the Earth, from Hawaii to Chile to Antarctica, all working together. By combining their observations, scientists create an Earth-sized telescope with incredible resolution, able to see the shadows of black holes, humans working together to see the unseeable. Taking a picture of a black hole requires enormous amounts of data, so much data that it can't be transmitted over the internet. It's faster to ship hard drives, physically, from one observatory to another. Tons of data, from observations made on the same night, all over the world, combined, processed, for months, and the result is a single image, a ring of light around darkness. Worth it. We can detect black holes through gravitational microlensing. If a black hole passes in front of a distant star, its gravity bends the star's light. The star appears to brighten, then dim. By monitoring millions of stars and looking for these brief brightenings, we can detect black holes, even isolated ones, not orbiting anything, not feeding, just passing by. In the night, LIGO detects gravitational waves from merging black holes. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses lasers to measure tiny ripples in spacetime, ripples smaller than the width of a proton. LIGO can detect them, and from these ripples, deduce the masses, the spins, the distances of merging black holes. It's an extraordinary achievement. Measuring the imperceptible, we've detected gravitational waves from dozens of black hole mergers, each one unique, each one telling us about black holes we could never see with light. Some mergers involve black holes more massive than we thought possible. Others involve black holes spinning in unexpected ways. The universe is teaching us that our theories were incomplete. Gravitational waves travel at the speed of light. They spread outward from their source, rippling through space, stretching and squeezing everything they pass through. But the effect is tiny, infinitesimal. Only the most sensitive instruments can detect them. They pass through us, through the Earth, through everything, harmlessly, gently, evidence of distant violence, arriving as the softest whisper. Future telescopes will see even more. The James Webb Space Telescope, will peer into the early universe, seeing the first black holes, the first quasars, next-generation gravitational wave detectors. We'll hear even fainter signals from even farther away. We're just beginning, just opening our eyes to the full population of black holes in the cosmos. There's so much more to discover. Humans have imagined black holes for centuries, even before we knew they could exist. Writers and thinkers pondered what would happen if gravity became so strong nothing could escape. In 1783, John Michell, an English clergyman and scientist, speculated about dark stars, stars so massive that light couldn't escape them. He was remarkably prescient, 2 centuries before we had the physics to describe them. The first mathematical solution describing a black hole came from Carl Schwarzschild in 1916, just months after Einstein published his theory of general relativity. Schwarzschild, a German physicist and astronomer, found an exact solution to Einstein's equations. He was serving in the German army at the time, on the Russian front, calculating in the trenches. He died shortly after, from an illness contracted during the war, but his solution lives on. The Schwarzschild radius, the Schwarzschild black hole. Einstein himself didn't believe black holes could actually exist. He thought they were mathematical curiosities, artifacts of the equations, not real physical objects. He was wrong, beautifully, wonderfully wrong. Even the greatest minds can be surprised by the universe. In the 1960s, physicists began to take black holes seriously. The discovery of quasars, the development of new mathematical tools, the realization that massive stars must collapse. Suddenly, black holes seemed not just possible, but inevitable. The universe demanded them. Black holes appear in countless stories and films. Interstellar, with its stunning depiction of a supermassive black hole. Gargantua, rendered with scientific accuracy. Star Trek, Doctor Who, the black hole. Countless science fiction tales. They capture our imagination, the ultimate mystery, the ultimate unknown, a place where the rules break down, where anything seems possible. The black hole in Interstellar was scientifically accurate. The filmmakers worked with physicist Kip Thorne to create realistic simulations of what a black hole would actually look like. The glowing accretion disk, the gravitational lensing, the way light bends around the black hole. It was so accurate that scientists published papers about it. New insights from a Hollywood film, art and science, inspiring each other. Stephen Hawking spent much of his career thinking about black holes. He made groundbreaking discoveries: Hawking radiation, the information paradox, the black hole thermodynamics. He showed that black holes aren't entirely black, that they have temperature, entropy, that they obey laws similar to thermodynamics. He brought together quantum mechanics, general relativity, and thermodynamics in profound ways. Hawking made a famous bet about black holes. In 1974, he bet physicist John Preskill that information falling into a black hole was lost forever, against the principles of quantum mechanics. In 2004, Hawking conceded. He'd come to believe information might be preserved after all, encoded in the Hawking radiation. Preskill won an encyclopedia of baseball, his prize. Even great scientists change their minds when evidence points a new way. Black holes inspire philosophical questions about the nature of reality, about what we can know, about the limits of science. If information can be lost, what does that mean for determinism? for causality. If we can never see inside, what does that mean for knowledge, for understanding? They push us to think deeply about the universe and our place in it. Many cultures have myths about cosmic voids, places of darkness, entrances to other worlds, boundaries between existence and non-existence. Black holes resonate with these ancient stories. They're the modern version, grounded in science, but still mysterious, still profound. Some truths echo across time. Let your mind rest now. You've come far. 70 facts, 30 more to go, but no rush, no pressure. Time dilation near black holes is extreme. If you orbited close to a black hole's event horizon, time would pass much more slowly for you than for someone far away. You might orbit for what feels like an hour, but when you returned, decades might have passed. Everyone you knew, aged or gone. It's not science fiction, it's real. A consequence of Einstein's relativity. This is called gravitational time dilation. The stronger the gravity, the slower time flows. It's been measured, confirmed. GPS satellites have to account for it. But near a black hole, the effect is extreme. Time can slow to a crawl, almost, but never quite, stopping. From Earth, we could never see something cross the event horizon. We'd see it slow down, redshift, grow dimmer, appear to freeze, right at the edge, but we'd never see it disappear. Not completely. The last photons would take infinite time to escape. From our perspective, the object would hover there, forever, at the threshold, but from its perspective, it crossed long ago. You could use a black hole as a time machine, theoretically, orbit close to the event horizon, experience time dilation, then return to Earth. You'd have traveled to Earth's future, aged perhaps a year, while decades or centuries passed on Earth, but you couldn't go back. Time travel to the future is possible. To the past remains a mystery. Some rotating black holes might contain closed time-like curves, pass through spacetime that loop back on themselves, where you could, theoretically, return to your own past. These exist in the mathematics, inside rotating black holes. But whether they're real, whether you could survive to use them, we don't know. The universe might have rules against paradoxes. The faster a black hole spins, the more it affects time and space. A maximally rotating black hole, called an extremal black hole, creates a region where you could orbit at the speed of light. The ergosphere, a region outside the event horizon, where spacetime is dragged so severely, you cannot stand still. You must rotate with it. You could extract energy from a rotating black hole through a process called the Penrose process. Drop something into the ergosphere in just the right way, and you can extract rotational energy from the black hole. The object that falls in can actually give you more energy back than you put in by stealing angular momentum from the black hole itself. An advanced civilization might use this to power their world, drawing energy from a black hole spin. Imagine that, if you're still awake. Black holes eventually stop spinning through Hawking radiation, through the Penrose process, through interaction with the surrounding space. Over unimaginable timescales, they slow down, lose their angular momentum, until they become still, non-rotating, simple. But again, this takes far longer than the universe has existed. Near a black hole, cause and effect can become unclear. The extreme curvature of spacetime can create situations where it's hard to say what caused what. Light can orbit, trapped in photon spheres, going around and around, neither falling in nor escaping. The universe, at its extremes, challenges our intuitions about time. Inside the event horizon, all paths lead to the singularity. No matter which direction you try to go, no matter how you fire your rockets, you move toward the center. It's not that you can't fight against it. It's that the singularity is in your future, in every possible future. There's no path that avoids it. You could no more avoid it than you could avoid next Tuesday. Let that thought be distant, abstract. You're safe here, in your bed. In the far future, black holes will be all that remains. After the stars burn out, after galaxies fade, after even protons decay, black holes will persist for 10 to the power of 100 years or more, alone in a dark, cold universe, slowly evaporating through Hawking radiation, bit by bit, over timescales that make the current age of the universe seem like an instant. As the universe expands, black holes become isolated, galaxies drift apart, accelerated by dark energy. Eventually, each galaxy cluster becomes alone, separated from all others by vast, unbridgeable distances. And within each isolated region, black holes wait, the final structures, the last things to exist. Small black holes evaporate faster than large ones. A black hole with the mass of the Sun would take 10 to the 67th power years to evaporate. A supermassive black hole, millions or billions of solar masses, would take 10 to the 100th power years or more. The giants persist longest, the last lights in a dying universe. As a black hole nears the end of its evaporation, it glows brightly. The smaller it gets, the hotter it becomes, the faster it radiates. In its final moments, it might shine brighter than a star, releasing all its remaining mass energy in a final burst of radiation. And then, nothing. It vanishes, returns to the quantum foam, the vacuum. After all black holes evaporate, the universe reaches heat death, maximum entropy, no temperature gradients, no energy flows, no change, just equilibrium, silence, the end of all stories. But that's so far in the future that it's almost meaningless, longer than you can imagine, longer than numbers can easily express. Some theories suggest new universes might be born from black holes, that the singularity doesn't end, doesn't destroy, but transforms, creates something new. Each black hole, a seed for a new cosmos, with its own laws, its own constants, its own story. If true, then black holes aren't endings, they're beginnings. Black holes might be the universe's way of exploring possibilities. Each new universe, slightly different, different physical constants, different particles, different rules, an eternal process of creation, an exploration, an evolution. The multiverse, born from black holes. It's speculative, beautiful, unproven, but it offers hope that endings are also beginnings. We don't know what came before the Big Bang, but some theories suggest our universe itself emerged from a black hole in another universe. We might be inside one right now, the descendants of a collapsed star in some parent cosmos. It's impossible to test, but it's a reminder that we don't know everything. That mystery remains. Black holes remind us of how much we don't know, about quantum gravity, about the nature of spacetime, about the ultimate fate of information. They're not just objects to study. They're questions, challenges, invitations to think deeper. And yet, we've learned so much. From pure theory, from from observation, from mathematics and philosophy and bold thinking. We've gone from not knowing they exist to taking their pictures, detecting their mergers, measuring their masses in just a few decades. A remarkable achievement of human curiosity and persistence. Black holes are among the most extreme objects possible. Within the known laws of physics, you can't have stronger gravity, you can't curve space-time more, you can't compress matter further. They're the limit, the boundary between what is and what might be beyond. They make us reconsider what's possible. Time travel, wormholes, other universes, information paradoxes, concepts that seem like science fiction become serious physics. When you study black holes, they expand our imagination, push us to think in new ways. Every black hole is unique, yet they're all described by just 3 numbers: mass, spin, charge. That's it. Everything else is erased, lost behind the horizon. It's called the no-hair theorem. Black holes have no additional features, no hair, just those 3 properties: elegant, simple, and yet containing infinite complexity inside. We may never fully understand what's inside. The singularity, where our equations break down, where infinity appears in our math. Perhaps there's something there, beyond the singularity, that we can't yet describe, that requires a new theory, a new language. Or perhaps the singularity is real, a true point of infinite density, where the story ends. We don't know, and maybe we can't know. Black holes teach us humility. They remind us that the universe is stranger than we imagined, stranger than we can imagine, that our everyday experience is just a tiny corner of reality, that extreme conditions reveal hidden truths. We are very small in a very large universe, full of wonders we're only beginning to understand. They also teach us courage, to face the unknown, to ask questions even when answers seem impossible, to keep searching, keep calculating, keep observing. Thousands of scientists, over decades, piecing together the puzzle of these invisible objects through cleverness and persistence and collaboration. Black holes connect us to the cosmos. The atoms in your body were forged in stars. Some of those stars became black holes. The carbon in your cells, the calcium in your bones, the iron in your blood, all created in stellar cores, scattered by supernovae, the same explosions that birth black holes, were made of star stuff, connected to everything, including the darkest objects in space. Looking at black holes, we look at our origins, the supermassive black holes that shaped galaxies, that regulated star formation, that allowed planets to form, life to emerge. Without black holes, the universe might look very different. We might not be here. In a way, we owe our existence to these cosmic phenomena. Black holes will outlive us, long after humanity is gone, long after Earth is gone, long after the sun burns out. Black holes will remain, silent witnesses to everything that was. They'll persist in the darkness for unimaginable eons, until finally, they too fade, the last remnants of a universe that once teemed with light. And yet, right now, we're here, in a universe with stars, and planets, and life, and black holes to study and wonder at. We're here, in this brief moment, when the universe is young enough to be interesting, old enough to be complex. We can look up at the sky, know that black holes exist, and feel awe, wonder, curiosity. What a privilege, what a gift, to be alive, to be conscious, to ask questions about the deepest mysteries and to find some answers. So there you have it, 100 facts about black holes, from their birth in the collapse of massive stars to their eventual evaporation in the far future, from the physics of event horizons to the mysteries that remain unsolved. Black holes, the most extreme objects in the universe, the darkest, the strangest, the most profound, and you, lying here in the quiet of the night, have traveled with me through space, through time, through the depths of cosmic mystery. I hope these words have been gentle companions, that they've eased you towards sleep, or already carried you there. If you're still awake, that's wonderful. Let your mind drift now over these ideas, these images, these distant, impossible objects. If you've already drifted off, then these words are just echoes, ripples, fading into your dreams. Either way, you're exactly where you should be. The universe is vast, full of wonders, full of mysteries we're only beginning to unravel. But tonight, you don't need to solve them. You don't need to understand everything. You just need to rest. Let the darkness of space mirror the darkness of sleep, both peaceful, both full of potential. Let the infinite depths of black holes remind you that some questions can wait until morning. For now, just breathe deeply, slowly. Feel the weight of your body against your bed, against the earth orbiting the sun orbiting the galaxy, around a supermassive black hole. We're all moving, all traveling through space together. But for tonight, be still, be at peace. Thank you for listening. Thank you for this journey. May these stories of black holes and cosmic mysteries guide you gently into the deepest, most restorative sleep. May you dream of distant stars, of curved spacetime, of light bent around invisible giants. Or may you dream of nothing at all, just rest, just peace, just darkness. Good night, sleep well, and remember, if you enjoyed this journey, subscribe to the channel, leave a like, so we can explore more mysteries together. But do that tomorrow, when you wake. For now, let the universe hold you. Let gravity pull you gently into sleep. Good night.